Hello everyone and welcome back to this Nanophotonics and Plasmonics course. Today is the third and last video for this chapter 2 and we cover a few very important concepts in nanophotonics. So the first one is actually dealing with the Dyadic Green function formalism. Dyadic Green functions or green tensors are just mathematical objects that allows to calculate the fields, whether if it's an electric field or a magnetic field, from a point source. So let's consider that you have, for instance, in here an electric dipole, which is a point source, and we want to calculate the electric field at a different location, which is induced by this point source. And we can do that using this green tensor. So this is the expression that relates the electric field from this point source or this electric dipole P with the green tensor. So we'll see what this green tensor is, what it looks like later on. But this is how this electric field is actually calculating from the point source with the green function formalism. So the complete derivation of this green function, and how we actually calculate that, can be done considering the potentials, so both the vector potential and scalar potential. So we first start by expressing the electric and magnetic fields as a function of those potentials. So these are the two expressions that are well known in electrodynamics. And then using those expressions, you can insert them into the Maxwell's curl equation. You can use the Lorentz gauge, and then this leads to two sets of Helmholtz equations, which are given here. So I'm not gonna spend too much time in this particular presentation to detail how we go from the beginning here to those Helmholtz equations. This is done in a separate video, so I encourage you to actually look at the other video in detail to see how you actually obtain the Helmholtz equations. Those two Helmholtz equations can be in fact expressed as four scalar Helmholtz equations. If you consider this, the first one here is actually applied onto a vector. So there's the vector potential, which can be broken down into three different components. So that basically gives you four scalar Helmholtz equations. Those Helmholtz equations are equivalent to the wave functions, the wave equations in frequency domain. So these are the equivalent of wave equations applied on those potentials. The right-hand side terms, which are going to be then represented by this function g, serve as the source, and this is the field that actually propagate from the source. So if you consider that this source is actually a point source, a single point source that can be represented by the Dirac function, then the particular solution that you're looking for, this function f, is actually called the Scalar Green function. So this is a particular solution of these Helmholtz equations when the source is a point source that can be represented by a Dirac function. So let's expand on that a little bit. Let's look at this Scalar Green function, what it looks like. So this Scalar Green function is these particular solutions. This is actually expressed as an exponential. So in fact we have two exponentials, so then in fact this contains two particular solutions. You have this exponential ik r minus r prime. So this r minus r prime is the distance between a point source and the locations where you actually calculate the local electric field. And then you have this exponential negative ikr, the same. So these are the two representations of those fields. So these are the fields emanating from these solutions. So you have in fact positive exponential that gives you an outgoing spherical waves being emanated from this point dipole, and then the negative IKR is actually converging an incoming spherical wave on this particular location. So these are the two physical solutions. So these are two spherical waves, outgoing spherical waves and incoming spherical waves, that are physical solutions in free space of a point dipole. So then you can actually go a bit further. You can actually look at what happens with the electric field and magnetic fields. And once they're involved, formalism becomes a little bit more involved and complicated. And instead of having just a scalar green function, you actually have to make use of a tensor. So the green function becomes a tensor, and it's what we call the dyadic green functions, or green tensor. So how do you actually calculate this green tensor? What does it look like? If you want to calculate the green tensor that relates the electric field induced by your point source, now basically you have to start from the wave equation. So we can start from the electric field. You can also start with the magnetic field, but we're gonna be doing this using this wave equation. And when you substitute the electric field by the green tensor throughout this wave equation, this is what you obtain. So the solutions, the electric field and the magnetic field, you can actually calculate from this green function formalism are given here. So these E node and H node are actually background fields. So if you have, for instance, an external background field which is independent on the charge distribution, current density distribution, these are just background fields. They can be zero, and then the fields induced by the current distribution is actually given by this integral here. So we have an integral over the volume of the current distribution times this green tensor. The same for the magnetic fields. It's not the simple product of the green tensor with the current density, but then there's the curl now this green tensor. You can actually show, and this is done in the textbook, that the dyadic green function is actually expressed as a function of the scalar green function via this operator. So this set of operators with the unit dyad, unit tensor, and then those nabla operators. So we'll see later on applications of this formalism. This is something we're going to be seeing several times throughout this course. We'll expand that into a greater detail, and then we're going to start studying some physics when we're going to talk about optical interactions in chapter 4. So something which is also very important in nanophotonics is the Lorentz reciprocity theorem. So this reciprocity theorem does not only apply to nanophotonics, it's something way more general. You can actually find this Lorentz reciprocity theorem first in the field of antenna theories. And it just simply states that the source and the detector of electromagnetic fields can actually be interchanged without affecting the physical situation. So we'll actually derive from scratch this reciprocity theorem. So I'm going to just show you the major steps here, and you can find actually all the technical details and the actual mathematical derivations with all the steps in a separate video. So we start first by describing our system, which is comprised of two current density distribution, J1 of volume V1, and the current density distribution, J2 of volume V2. And this can be described using Maxwell's curl equations. We have two sets of Maxwell's curl equations, electric and magnetic field for the first distribution, and electric and magnetic field for the second distribution. So now we can manipulate those equations a little bit. We can actually multiply each of these equations by complementary field. So I discuss more in details about this in the other video. We can actually then just sum up those two equations, electric and magnetic field, for each distribution separately, and then you take the difference between those two quantities. With that, you obtain an actual expression which is which is discussed in greater detail in the second video. And then you take a mixture of Gauss theorem and physical insight, and then you end up with this final expression. So this final expression is the reciprocity theorem. So what it states basically is that if you have a source J1 and you detect the field E2, which is basically the field at the other location on the other side, it's exactly the same as if you were actually looking at the source J2 and looking at the field J1. So let's look at this a little bit more carefully in the next slide. So the equation is, as I said, is widely used in antenna theory, but also here in nanophotonics. So what we can do is actually also express these electric fields E1 and E2 that are in those in this reciprocity theorem in terms of source and currents. So we've seen just a moment ago that the electric field can be calculated from a source, a point source, using the Dyadic Green tensor. So note that here the background field is set to 0. Okay, so there's we make it simple. There's no background field. The electric field we calculate, the total field we calculate, is the induced field from the point source. If you inject this expression into the reciprocity theorem, which is just above here for E1 and E2, basically you end up showing that the green tensor, the element of the green tensor of R1, R2 is actually equal to the green tensor element R2, R1, which simply implies that the green function is symmetric. This has a clear physical implication. So this means that if you were to calculate the electric field E1 at location R2 from a current density J1 using this green tensor element R2, R1, then this is totally equivalent to looking at the electric field E2 at position R1 from the source J2, which is located at R2, via this symmetric element R1, R2. So this is totally equivalent, and this is the reciprocity theorem illustrated in its full potential. So we can flip the source and the detector in position, source and detector, and you will actually not change the physical implications of this. So this is exactly, we're going to discuss that in details when we're going to talk about nano antennas. This is exactly the principle that actually make antenna possible. So those the antennas you have on your rooftop or on your car or on your cell phone are allowed to actually emit radiations and receive radiations. And this is the underlying physical principle behind it. So finally, the last subject, the last topic I wanted to talk about, evanescent fields. So the evanescent fields are a special type of fields that we're going to see quite extensively throughout this course. So evanescent fields can be described as just regular plane waves, which can be expressed just as an exponential. So you have the amplitude of the field E. If you're looking at an electric field, for instance, the same for magnetic fields. Exponential I kr, so k being the wave vector, r being the position, minus omega t, so the frequency and the time. So these are regular plane wave expressions. However, an evanescent field is this plane wave where at least one component of the wave vector k is actually imaginary. So what happens when this is imaginary? So if one of the component of k is imaginary, then the exponential I kr becomes real exponential. So therefore means that the field is actually not propagating along that particular direction, and the field decays exponentially in that direction. So let's look at this into more details in a minute. So those fields do not occur in homogeneous media. So if you have a homogeneous media and you have an electric field, you can only have propagating fields and stationary fields. You do not have evanescent fields. Those evanescent fields, are actually connected to inhomogeneities. More specifically, when you have interfaces. So, for instance, you have a planar interface between two different media. So this is the case, for instance, if you have, let's say, for instance, a glass substrate and it's covered by air, and if you send light with a given polarization, we have this P polarization for this electric field incoming onto this this interface. For a particular condition, this interface will actually reflect some of the light, some of this electric field, and thus the condition is actually going to transmit. And for some specific cases, we can have actually an exponential decay of the field at the surface when moving away from the surface. So in this particular case, we're gonna, for instance, have the z component of the k vector, which would be imaginary. So along the z direction, this electric field will actually decay exponentially along the z direction, but can still propagate along the x and even the y, the out of plane y component directions. So you can actually calculate also what's the critical angle for which this happened. So this critical angle is the arc sine of 1 over n, which is the relative refractive index between the two media. So this is dictated by the composition of the materials on either side of the interface. So for non-absorbing media and for this supercritical incidence, when this angle of incidence is actually larger than the critical angle, there's actually a total internal reflection. So all this electric field will be reflected. When you are at the critical angle, when this incident field is actually following this critical angle, then the electric field is going to remain at this interface as the form of evanescent wave. So there's no net transport of electromagnetic radiation in a direction normal to the surface. So that's going to be something very important that we're going to actually discuss in a second. When this all the electric field is actually being reflected, this is known as total internal reflection. This is the principle, for instance, of optical waveguides. So if you have optical waveguides, such as optical fibers, this is the principle on which this work. So we're going to discuss optical waveguides and photonic waveguides and plasmonic waveguides later on during this course, but the optical waveguides work on this principle of total and internal reflection. So all the light is basically bouncing off this interface. So if you consider a waveguide where you have one interface on one side and one interface on the other side, the light will bounce back and forth at this particular angle of incidence all the way through the optical waveguide with minimal loss. So we can actually show that there's no energy transport along the direction normal to the surface, to the interface. This can be shown via the pointing vector. So you can actually calculate the z component of time average pointing vector, which is 1/2 of the real part of this term. You can actually calculate that, and you're going to see that this vanishes. So there's no net energy transport across the interface. The energy, however, is transporting along the interface. So that doesn't mean that this evanescent wave does not carry any energy. This evanescent wave carries energy, but it just stays at the interface. So you can actually calculate the x component or the y component of this pointing vector, and you can actually show that this is non-zero. So this term is actually showing that the evanescent wave carries some energy, but along the interface and not across the interface. This is, for instance, an experimental realization of this total internal reflection and evanescent waves. So you can have this incoming wave arriving at the interface and then being reflected as a total internal reflection, and there's no light being transmitted. And this is actually also showing that there might be some fields here at the surface for some of these incident angles. So I will just show you numerical simulations for these different conditions. So if you look at an interface between a medium at the bottom of index 1.5 and air at the top, this actually will show you how this evanescent wave are formed. So on the left-hand side, you have a wave which is being transmitted. So this is a plane wave, incoming plane wave being transmitted because the angle of incidence is below the critical angle. Here we have the formation of those evanescent waves. So you see that this evanescent wave stays at the surface because we arrive with an angle of incidence which is the critical angle of 42 degrees in this particular case. And those evanescent wave stays and decays exponentially. And the last one is this total internal reflection. So we have an angle larger than the critical angle, 45 degrees or 50 degrees, and then it's just bouncing off the interface, and nothing is being transmitted into the air on the upper half space. So these are the three different conditions: total transmission, evanescent waves, and total reflection, total internal reflection. For the same plane wave at the same wavelength. So this is a 500 nanometer wavelength plane wave incident at different angles on this glass air interface. So that concludes our third video pretty much, and our chapter 2. So we've looked at throughout this chapter 2 Maxwell's equations. We discussed about the conservation of charge, wave equations, and total current density. We discussed about those wave equations. We discussed about the constitutive relations as well, which are very important. That they describe what the material does in the presence of electromagnetic fields. We discussed about the spectral representation of the fields, introduced the complex dielectric permittivity. Boundary conditions as well form a very important aspect of nanophotonics due to the presence of interfaces, and we discussed the Fresnel coefficients for calculating the reflection and transmission. Conservation of energy, discussed extensively about the Poynting theorem, which we've just seen an application of to actually calculate the net energy flow through an interface at the critical angle. And we discussed extensively also this green function formalism, introducing both the scalar and the dyadic green functions, and the reciprocity theorem and its implication on the symmetry of the green function. So this is something we're going to be using also extensively throughout the course when talking about optical interactions. And finally, we introduced the concept of evanescent waves that are also forming at an interface in the case of total internal reflection when we are near or above the critical angle. Finally, I wanted to finish up with a minor side note. So I mentioned both the Lorentz gauge and the Lorentz reciprocity theorem, which have been spelled differently. So they come from two different scientists, two different physicists. So Ludwig Lorentz was a Danish physicist, and he's the one who gave its name to the Lorentz gauge in electromagnetism, and the Lorentz mean theory that we're going to be discussing in Plasmonics chapter. And Hendrik Lorentz with a T is a Dutch physicist, which gave its name to the Lorentz reciprocity theorem, but also to the Lorentz distribution. Lorentz force, and for instance also in the Lorentz transform